Hello everyone, welcome to our discussion of section 5.2 where we will be talking about the definite integral. Now before we get into the definite integral, we should discuss what is an indefinite integral. But the definite integral, notation-wise, is what you see on the screen, with this long S shape notating the integral, and then the A and B are the lower and upper limits of some interval over which we want to integrate a function. Now it's interesting because in the remainder of chapter 5 in this semester, we're going to just basically introduce the concept of the integration, and then, as I mentioned in the other video lessons, in Calculus 2 is where we really apply the integration of a function itself in an expansive way. But until then, the section 5.1 and 5.2 are basically dedicating themselves to making sure that you understand what a concept of integration is. And then after that, we will see more details of the integration. So this is the main topic of our discussion in this section, the definite integral. But let's just quickly talk about what is an indefinite integral. So at least we know the difference and we know how to recognize one from the other. So the indefinite integral has these limits missing. And of course, that's huge. That has huge implications in terms of what the difference between indefinite and indefinite integral. So an indefinite integral would be like this: integral of function f of x dx, and that would be indefinite. Notice that the limits are missing from this integration. But what implication would this have? Well, if you have a definite integral, this represents a value, a number, a single number. It represents a single number. Whether that's a positive number or a negative number, it makes no difference. But a definite integral, once you're done with it, represents a single value. But the indefinite integral, it represents, with the limits missing, it represents not a number, but a family of functions. So it would represent f, I'm just using the capital F for the antiderivative, f of x plus c. So these are a family of functions. Notice the huge difference here. The limits are missing. The lower and upper limits are missing from the indefinite integral. And instead of representing a number, which is what the definite integral does, we have a family of functions. Okay, that's a huge difference, right, comparing the two. Now you might say, well, how do we have a family of functions if this, whatever function, it's going to give us the same antiderivative? Where is this family of functions? Well, this family of functions is distinguished from one another. Each member of the family is distinguished from one another by the value of this constant. Because if you take the derivative of this function, and if that constant is 100, you're going to get the same derivative, which would be f of x, as if you had c equaling minus 20, you would still get f of x, even though the c values or the constants are different. In the parent function, the c values are different, but the derivative would be the same. So the distinguishing element among the different family members of this function are dependent on the value of that c. So let's just make a note of that. So here, the constant value distinguishes different functions, okay, among this family of functions. All right, so what would be an example of an indefinite integral? You've seen this before when we talked about antiderivatives, but let me just remind you, this would be an example. Suppose we have the integral of, let's say, x to the 4. Let's pick an easy one, x to the 4th plus 3x minus 9 dx, right? This is clearly an indefinite integral because it has its lower and upper limits missing from the integral notation. So we can easily calculate the antiderivative of this, or the integral of this, and we get 1/5 times x to the 5th power plus 3/2 of x squared minus 9x, and of course plus c, right? C. So now that when you take the derivative of this to obtain that, there are infinitely values for c you can pick, right? And those infinitely many values of c give the family of functions of this form that would have the same derivative. Okay, so that would be an example of an indefinite integral. So now back to our discussion about the definite integral, which has this notation with the clearly defined lower and upper limits. Then remember that in section 5.1 we discussed the Riemann sum, right? So let's then write an equivalent of this in the form of some kind of a definition that involves the Riemann sum. Okay, so we will do that. So let's say it this way. If a function, let's call it just f, a function, well, if a function is defined, first of all, let's give it the domain, is defined on some, let's say, interval a to b, right? I'll just use these letters to match what your book has, so that if you read this or watch this and read the book, the notations and letters match. So if a function is defined on some interval a, b, that means when we say defined, we mean if a function is continuous on this interval, right? So it's defined everywhere. Then the definite integral of f from a to b, or over this interval from a to b, is the number, right? We already mentioned that the definite integral represents a number, so there it is. It is equal to the integral from a to b of the function f of x dx equals limit of n, as n approaches infinity, of the sum with the index going from 1 to n of f of x sub I times delta x. Remember that from the section 5.1, right? Our discussion of the Riemann sum there. So you can also look at this as the definition of the integral, but I will mention this again, and we will do examples of calculating the definite integral using this Riemann sum. Okay, so we will do plenty of examples using regular integration methods, but we also apply the Riemann sum to that, so we have a good, well-rounded picture of what integrals actually do. Okay, so, and talking about what integrals do, then given that definition, we have that this portion and integral of a to b of function f of x to dx represents the area, or the net area, I should say, represents the, very important, this is the net area. Net area refers to the summation of several areas. And in this context, if an area region under the curve, between the curve and the x-axis, is below the x-axis, we refer to it as the negative area in order to distinguish that from the portion of the curve, area under the curve that is between the curve and the upper positive side of the y-axis, then we refer to that as a positive area. So any area region between the curve and the x-axis that is below the x-axis, or along with on the same side as the negative side of the y-axis, we refer to that as the negative area. And any area segment that is above the x-axis or along with the positive side of the y-axis, we refer to that as the positive area region. And the net area is those two regions added together, whatever value or number we get after we add the negative area plus the positive area. Okay, so it represents the net area. And I'll just write what I said. Below or above the curve. Let's just give an example as shown in the figure in the next page, because I'm going to run out of room here in the figure on the next page. Okay, so let's quickly draw that. So here we have, and I forgot to bring my ruler, so I hope I can draw these straight lines. So we have a graph that looks like this, and also our y-axis, or f of x, let me call it, f of x equals y. All right? And then suppose we have a curve that does this. So it goes like this, and then it does that. Okay? So clearly, we have an area between this curve and the x-axis that is below the x-axis, right? On the same side as the negative side of the y-axis. So let's call this, and I'm going to use my thick marker here to call this A2, and A2 has negative value, right? It's some just for, so this is some negative value, A2 let's call it. And then A1, which is the area under the curve above the x-axis, and I will just drop a dashed line here. So this segment, which is above the x-axis, let's call that A1. And that's, of course, because it's above the x-axis, we take that as the positive area region. And let's call this function f of x, if this is some function f of x, then the integral of this would be, so it would be a to b, and I should identify what a and b are on this graph. A is the lowest limit, which would be here, a, and b would be here, right? The lower and upper limits of the definite integral. And then f of x dx is simply the net area under the curve, or between the curve and the x-axis. So it would be a1 plus a2. Okay, so we know that that area is negative, this area is positive. When you add them together, you will get some number there that would represent the net area, okay, from A to B. Okay, so that's a basic look at definite integrals. All right, so then, having said that, we should look at some properties of definite integrals. Okay, so this definite integral has some properties. I think I should be able to fit all these properties on the remainder of this page, so let me do that. And we will say these are properties of the definite integral. Okay. All right, so these are very, very important, especially those of you who will move on to Calculus 2 will make extensive use of these properties, as well as in this course in the remainder of chapter 5. So here's one of the properties. If we have the definite integral from A to B of some function f of x dx, that is equal to, you can so this would be minus, right? As soon as you put the minus in front, then you can switch the limits of this definite integral. So that is equal to a minus a to b. Notice the limit, the lower and the upper limits of the integral swapped spots, because we put this minus in front. That has that effect of f of x dx. Okay, so that's one of the properties. Of course, if you move all the way to Calculus 3, you'll see many, many applications of these properties that we introduced today. So these are some things that you don't want to forget, these properties. They are very, very useful. Another one is that if you have integral limits that are equal to each other, so a to a or b to b or something like that, then the integral value is going to be 0 because there's no area, right? Remember that the definite integral represents the area between the net area between the curve and the x-axis when it's dx. And if it goes from the same limit, lower limit to upper limit, let's say a to a, then there is no area under that, right? So f of x dx is equal to 0. Like that. Then we have a property that says if we have a definite integral from a to b with a constant value in here and dx times dx, this constant can come out and in front like that, and then it can multiply itself by b minus a. So that's another property. I should probably use a scratch paper to show what this means. See, if you have, so let's just rewrite this. Let's just rewrite this as c times the integral, right? We can do that. ba and then dx. Okay? Then this piece is equal to c times x, because the integral of dx is just x, right? Because we have a 1 here. There's a 1 here, and if you integrate 1 dx, you get x, right? The derivative of x is just 1, and that's what we have. We're finding the antiderivative of 1, which will give us x, but we have the limits of integration here, a to b, and this translates into b as we evaluate x at these values. So b minus a. That's what I've written in red ink is this quantity, of course, times c. So that's what we have here. Okay, so if you have an integral of definite integral of a constant, this is what you're going to get. Simply multiply the constant by the difference between the upper and the lower limits of the integral. Okay, then the next property is if we have the summation in this form. I guess I should write it here. Or maybe I can fit it here. Let me just try. So the definite integral from a to b of f of x plus, let's say, g of x dx is equal to a to b, integral of a to b of f of x dx plus integral of a to b from a to b of g of x dx. So in other words, you can apply this definite integral to each one separately as it is, as you can see on the right hand side. So this would be another property. You can go backwards too. You can go from this side to that side, or from that side to this side. Okay. Another property that we should mention is that if you have a constant, the next property is kind of connected to this. They're very closely connected. So if we have the definite integral from a to b of some function that is multiplied by a constant, maybe I should put this constant in red so it stands out, that constant of and dx, then you can put this constant in front. It doesn't have to stay in the integral. It helps in the simplification of integrals, as you can see later. So then that c can come out in front and then multiply itself by the definite integral of f of x dx. Okay, and we can say c is any constant value. Okay, so that's another property. Another one, so we said that if you have summation of two functions in a definite integral, you can separate those and apply the definite integral to each one. You could do the same thing for the minus kind. As a matter of fact, let's just make the safe space on paper and let me add a minus here, because I can rewrite this with plus minus, but we can do it right here and then minus. Okay, so this property applies to whether we have an addition or a subtraction here in between the functions. Okay, so that's two properties in one. What else do I have here? Let's see. Okay, so this one is really useful property too. That if we have, let me actually describe this because I have to give a description of this. Suppose we have some interval, let's say a, b, a closed interval, a to b, right? A comma b. And let's suppose that c is some number in this interval. Suppose c belongs to, that's the notation, mathematical notation for belonging to a set. C belongs to this interval a, b. So c is somewhere between a and b, right? Because a is the lower limit, b is the upper limit. So c has to be between, if c is in this interval, it has to be between a and b. If that's the case, then we can write this integral. We can say that, let me suppose that, then, or thus, this is what we can say. We can say a to c a to c of f of x dx plus, so if c is in the middle, then a to c would be an area, and then plus from c to b, right? From c to b of f of x dx is the same thing as if you take the net area from a to b of f of x dx. I hope you can see how this side is equal to that, right? With c being in the middle. So a to c plus c to b is the same thing as going from a to b. Okay, like that. Well, I think that's all the properties. Oh, but there is some, I should list this and then relist it again later because these are such important. And in calculus 2, you will use these again a lot. When we calculate definite integrals, we need to know some three sums that are very, very important. There are proofs of this, but in this class, we're not emphasizing the proof of these, which are very simple, by the way. But we're just going to be able to remember and use them whenever appropriate. And these are these sums. So let me just title this as useful sums. I like to fit all this on one page so when you study, then you have them on one page rather than scattered on multiple pages. So we have, if you take the sum of, I as I goes from 1 to n, that is equal to n times n plus 1 over 2. I believe that the first time that anybody used this sum was Gauss when he was 8 years old, and at least that's what the story is, that when he was 8 years old, his teacher asked everybody in the class to add the first positive 100 digits, and he could quickly do that by using this this formula. So this, I don't know if that story is true, but for sure we can use this in our work today. So one is for sum of I as I goes from 1 to n. Another one, useful one, is for I, sum of I squared is equal to n times n plus 1 and times 2n plus 1 over 6. So let me, so goes from 1 to n again, right? And then, so that's another one, useful sum. And the next one, I'm sure you guessed it, has to do with I cubed. So sum of I cubed as I goes from 1 to n is equal to n times n plus 1 divided by 2, all of that squared. Okay, these three sum formulas are very useful, become very useful sometimes when we are dealing with definite integrals. And I will mention these again because they're important. Okay, so let's, I guess before we get to some examples, we have another set of identities, at least a few more identities to talk about. So these are all very useful as we work in this topic. So let's then, this is comparison properties are called, at least your book calls them that, comparison. I'm not very keen on remembering all these names, but to apply them is very important. So comparison properties of the definite integral. Okay. So what this is saying the comparison properties are as follows. If we have a function that is equal to or greater than 0, in other words, it's always positive, right? It's either equal to 0 or positive. For some interval, let's call it, I will just describe it as your book describes it, for x between and equal to a and b. Or you can say just closed interval a comma b. You can also write this as that. If this is the case, then what we have is that the definite integral of function f of x dx is also greater than or equal to 0 over that interval, and this time I'll just switch notations so these two are the same thing, right? So if the original function is 0 or greater than that over this interval, then the integral of that function is going to be greater than or equal to 0 as well. That makes sense, right? Because if a function is always greater than or equal to 0, and let me see if I can bring back my scratch paper here. So if a function is always greater than, sorry for this, and this is just my scratch paper. So if you have a function that is like that, from a to b, it doesn't have to be over the entire course of the function, but from some interval, a to b, let's call it, then the definite integral represents the area under the curve, right? And because the function is always over from a to b is greater than 0 at all times, then the area under it will always be positive as well, right? So using this quick graph, we can show that it makes perfect sense, given our definition of the definite integral, right? So then, if f of x is greater than or equal to some other function g of x over some interval, let's say a to b, for x being between a to b, then I'm sure you guessed what this property is going to be, right? So the definite integral of f of x is going to be greater than the definite integral of g of x over the same interval, right? So let's write it down. Thus, or then, definite integral from a to b of f of x dx is going to also be greater than or equal to the definite integral of g of x dx. Okay, that's that. And then one more property. So if we have, and now this goes back to our discussion of in section 5.1 when we talked about the Riemann sum. We talked about lower sum, Riemann sum given the left endpoints and the right endpoints. Remember that? The left endpoints represented the lower sum and the right endpoints represented the upper sum. So, of course, that's for, it will vary depending on whether we have an increasing or decreasing function, right? We talked about it in detail in section 5.1, which one would give us the upper sum or the lower sum. As far as the left endpoint or the right endpoints are concerned, it depends on whether we have a decreasing or increasing function, which we covered in section 5.1. But if we have m, and let's think of m, lowercase m, as the lower sum, being smaller than the function value, and function value being smaller than capital M, or the upper sum, over some interval. For some interval, again, let's take it as from A to B, then we can say that M m times b minus a, that's the upper limit minus upper limit minus the lower limit, it's going to be, well, it's going to be less than or equal to the value of the definite integral from a to b, less than or equal to, right, f of x dx, and that's going to be less than or equal to the m, capital M, or the upper sum times the difference between the upper and the lower limit of the definite integral. So, so let me that m times b minus a. Okay, so these are, and also let's box these. Like that. Of course, those are the conditions that have to be true before that relation or that property of the definite integral can exist. Okay, so those are the conditions. And let me just mention, so I'm going to say recall this lowercase m. Recall that this is the lower sum. Okay. And lower sum, and that one that this is the upper sum, or lower sum estimate of the area, and I'll say that here as well, estimate of the area. And recall that this is the upper sum estimate of the area. Let's say, so upper sum. Okay, so that just refers to that. All right, so having talked about all these concepts and definitions, let's go over some examples which helps us better understand the applications of what we just introduced. Okay, so we have, here's our first example. Suppose if we have a function f of x equals x squared minus 2x over some interval from 0 to 3, closed interval from 0 to 3, given that we want to evaluate the Riemann sum, right? We talked about this. It's coming back again. Talked about it in section 5.1. The Riemann sum with n equals 6. Remember what n was? N is the number of rectangles that we use to calculate the Riemann sum. The number of intervals which give us the rectangles under the curve. And then with n equals 6, so that's what we need to do, taking the right endpoints. They want us to do that, taking the right endpoints and or the upper sum for constructing the rectangles. I should, however, qualify this. The right endpoints will give us the upper sum only when we have what kind of a function? Do you remember from that discussion in section 5.1? Only if we have an increasing function. Okay, if we have a decreasing function, then using right endpoints will give us the lower sum. So this is apparently an increasing function. So for constructing the rectangles, and then they also want us to answer this very easy question. What does the Riemann sum represent? Does the Riemann sum represent? Okay, like that. I guess, I mean, they're not asking us to draw a picture, but why not do it? Because it helps us better understand this Riemann sum itself. So let me do that. Let me draw a picture here. I guess it would be, if I could just draw it here, like that. So let's call this x, and then f of x. And this is from 0 to 3, right? So I'm going to dedicate most of this blank space to the positive because we have nothing of the area that is on the negative side, right, going from 0 to 3. So I'm going to just do this, like that. And this is f of x, or y. And then if we graph this function, and I already have, we get something like this. We get, so we get, how do I, so I guess, like that, something like that. Okay. From 0 to 3, that is. So this would be, so let me mark this as 3, because that's the interval we're interested in, from 0 to 3, right? And then I try to draw this as symmetric as I can, and they want us to use Riemann sum with n equals 6, so 6 rectangles. So I will try to divide this distance from 0 to 3 to 6 equal spaces as much as I can. Okay, so that 1, 2, 3, and then I don't think they'll be that equal, but I'm trying to make them equal like that, roughly, right? So then this would be 1, 2, 3, 4. Oops, sorry, 0 to 3. No, this would be 0.5, and then this would be 1. 1.5, 2, 2.5. So this would be 1.5, and this would be 2, that one, and then this would be 2.5. Sorry for that little miss here, but each increment is 0.5 units wide, okay, from 0 to 3. So we have that. Then they want us to use right endpoints. So let me, well, again, I forgot to bring my ruler, sorry. So I'll try to do this by hand. So from 0 to 0.5, right endpoint, using the right endpoint would mean that I have to be here on the right endpoint of this rectangle from here to here has to be on the curve. So that's what I'm going to draw. Then for this one, so it would be a little bit higher maybe, or maybe the same level. So like that, like that, like that. And then that one, so this is, this would be, I don't know if maybe that, somewhere here. And that would be that. And maybe I don't have my pencil, but maybe I can just do this. So that's one of the rectangles, that's the other one, and that's the other one. And then other rectangles would be, so the right point here over this, oops, I should have drawn that dashed, but it's okay. So on that side, and then like that. So that's the right triangle, right rectangle there. And then above this, that's the right side there. And then let's drop it here. And then, of course, from here to here with the right point here on the curve. Okay, we did this in section 5.1, so at least we did it in a more detailed way there, like that. Okay, so this is our 6 rectangles that we have. Then the delta x, so the Riemann sum would be, let's just recall, and this is the solution. So we have, so recall that Riemann sum using the right endpoints, 6 of them, would be equal to sum of 6 rectangles of the function times delta x. Right? Delta x, of course, is the width of each rectangle, which should be equal to each other. How do we get that? The difference 3 from 0 divided by 6 intervals, right? So let's calculate that. So this is from section 5.1. So that's recall. And then we have delta x then would be equal to 3 minus 0 divided by 6, right? So it'll be 1/2. The width of each interval, as we expected, as I'm showing on in the graph, 0 to 0.5, 0.5 to 1, 1 to 1.5 is half, right? 0.5. Okay, so we have that. Then f of x, these xi's, so these are the function value at each right endpoint for these rectangles, right? So these are the ones we want to include here. So because we're taking the right endpoints, so we're going to use that f of xi for this point will be f at 0.5. Right? At that point, it'll be f at 1. Those are the right endpoints for each rectangle. Here, it would be f at 1.5. Here, it would be f at 2, f at 2.5, right? And f at 3, of course. That's the right endpoint of this rectangle. Right? So 1, 2, 3, 4, 5, 6. We have our function valued, which we need to calculate at these points, which are the right endpoints of each rectangle. And then we multiply all of that by delta x, which is 0.5. Let's do that. And so I'll just draw an arrow here, from here to here. Okay. So hopefully I can fit it across the page here. We have the Riemann sum of 6 rectangles, and delta x, right? Delta x times f at 0.5 plus f at 1. I'm just listing those in an equation. F at 1.5 plus f at 2 plus f at 2.5 plus f at 3. Okay. So then I guess we can calculate. So we evaluate this function at each of those points. So this is what we get. We get Riemann sum. Delta x is 1/2 or 0.5 times this function. Let me write it so it's on the screen, because it's right now off the screen. So this is the function we're evaluating at each of these points, like that, right? So we can, I hope I can fit it all here. So we have 0.5 squared minus 2 times 0.5, and that's just that, plus that function evaluated at 1 squared minus 2 times 1, like that, plus that function evaluated at 1.5, plus and 2 squared minus 2 times 2, plus 2.5 squared minus 2 times 2.5, three squared minus 2 times 3, like that. Okay. All right. So if we, and please double check these numbers. If we calculate those, we get these. So 0.5 times minus 0.75 plus or minus 1 and minus 0.75 again, plus 0 plus what is 5 over 4? So we have that one. I should, one moment, let me grab my calculator for that. So we have, I have 5 over 4, but I need to be consistent, I want to convert that to decimal value. So 5 divided by 4, 1.25. I should have known that, so 1.25. And then what else do we have? So we have plus 3. And that's that last one. 9 minus 6 should be 3. So adding all of those and multiplying it by 0.5, and let's see what do we get. So I'm just double checking this with my small calculator here, this one. I have to tilt it for you to see the screen. And when I do that, I can't write at the same time. So let me do this off this screen. I'm just adding all of these, double checking to make sure that I get 0.875 when I'm done with this. So minus 0.75 minus 1 minus 0.75 and then plus 1.25 plus 3 times 0.5. Yeah, that's correct. So we get 0.875. Okay. So that, and then they say, the last thing they asked us is, what does the Riemann sum represent? Okay, so let's just write it down here. Rectangles above of the three rectangles below the x-axis. So below okay, so That's why basically what it represents. There is or the net area, right? The sum of what I've just described is the net area. So this is the net area. Okay. The other thing that this book talks about in this section is the midpoint rule. So we should say something about that as well. So if we have the definite integral from a to b of f of x dx, that is roughly, again, applying the summation, or calculating this definite integral using the summation of those rectangles, using the midpoint of those rectangles, is roughly equal to the sum of those rectangles for the midpoints, that xi here. Well, actually, so let me that, and then where x, that notation represents the, well, it represents the midpoint, xi minus 1 plus xi divided by 2, and delta x is the number of rectangles, b minus a over n, which we've been doing since section 5.1. But then this is not using left endpoints or the right endpoints, but using the midpoint of each interval, each of these n intervals. We did one example in section 5.1 involving the midpoint of the rectangles, right? So please refer back to that in case you, just to refresh your memory on that. So let me, then that, xi with a bar on top, represents the midpoint on any interval from that. So these are the smaller intervals, right? xi minus 1 to xi. So each of those little, so this, let me actually use this graph that I had. So for this interval in this graph, xi minus 1 would be that, and xi would be that. So add those, divide by 2, you get the midpoint value. For this interval, again, xi minus 1 would be that point. Xi would be the upper point. Add those two, divide by 2, you get the midpoint. And this is really simple. And let me just bring back my now notorious scratch paper, right? Suppose you want to calculate the midpoint of 2 to 4, right? Just to make the point, let's pick an easy one to make a point. How do we know what is the value of this midpoint of a line segment between 2 and 4? So 2 plus 4 divided by 2, and that gives us 3, right? So we know m is equal to 3, which of course we know to be true. 3 between 2 and 4. So that's the same thing we're doing here with these rectangles. So to figure out where is the midpoint, we take the lower limit, 1.5 plus 2, 3.5, divided by 2, we get 1.75, which would be the middle of that midpoint of that rectangle. Okay, so that's what that formula really is saying. What we already know, but it's in the formula form. And this is the number of rectangles we have. Okay, so all right, so then I have to actually add a note here. Let me, since I wrote this note in blue, let me also make this note in blue. Note to to find xi's, right? To find xi's, first calculate a delta x value. Okay? And we'll do examples so you'll see how this works. All right, so this is the midpoint rule. We're using this, I mean, this is extension of section 5.1, that discussion, and we're adding on top of that. And the additional part is the definite integral part. But we did all of this in section 5.1 rather graphically than numerically. This is all numerical or symbolic representation of what we did graphically in section 5.1. That is, if you're wondering what's happening here as opposed to section 5.1, it's just that we did this graphically in section 5.1. Now we're doing it symbolically and numerically. Okay, so let's apply this to an example. So we want to, they ask us to use the midpoint rule with the given value of n. Because as you know, we can divide that area under the curve to however many rectangles we like. So with the given value of n, to approximate the integral, and it says round your final answer to 4 decimal places. Okay, so here is the example that we are doing. And I think there's just, so here it is. So we have the definite integral from 0 to pi over 2 of cosine to the 4th power of cosine of x to the 4th dx. And they want us to use n equals 4. So 4 rectangles. Okay, so so this distance is pi over 2 minus 0 divided by 4 will give us what? Will give us the delta x, right? So solution here. So delta x would be the upper limit, pi over 2, minus the lower limit of the definite integral divided by 4, and we get pi over 8, right? So that's the width of each rectangle. That's going to be that. Okay, so where are the endpoints then? So let me actually, the width of each rectangle. And by now you know which rectangles we're talking about, right? I'm not going to draw the graph on this one, but these are the rectangles we're talking about. The width of these is, in this case, it was 0.5, right? Now, in this example we have, it's going to be pi over 8. Okay, then, so, and then the endpoints, thus, the endpoints are as follows. So we have, I'll just use red ink, are at 0, of course, then pi over 8, right? Add pi over 8 to 0, you get that. What's the next endpoint? Add pi over 8 to that. You get pi over 8 plus pi over 8. Simplify it, you get pi over 4. Then add another pi over 8 to this, you get the other endpoint, and so on. So, and then you have to take the common denominator. So then you get 3 pi over, please double check these, and then you get the next one, the last one is pi over 2, right? Which is what you expect to have. Pi over 2 is the upper limit. Okay, then, of course, these are the endpoints, but we're not using the endpoints in our estimate. What are we using? We are using the midpoints, right? And we just explained how to calculate the midpoints. You add these, and you divide it by 2. Add these two, divide by 2. Add these two, divide by 2. Just like what I did with the midpoint between 2 to 4. Add 2 and 4, 6 divided by 2, you get 3. Which 3 being the midpoint between 2 and 4. We're doing the same thing, but we're doing with these values. Okay, so then thus, the midpoints are, so add these two, for example, divide by 2, you get pi over 16, right? So the midpoints are pi over 16. Add these two, pi over 8 plus pi over 4, divide by 2, you will get 3 pi over 16. Add these two, pi over 4 plus 3 pi over 8, divide that sum by 2. After simplifying, you're going to get 5 pi over 16. 3 pi over 8 plus pi over 2. Add these two, divide by 2. You get 7 pi over 16. Okay, I just wrote that so we save space, but that's what we did. That's where these come from. So, then using the midpoint rule, let's calculate, let's approximate the value of that definite integral, which is, let me bring this down a little bit. So we have 0 to pi over 2 of cosine of x to the 4th power dx is equal to the delta x, right? Let me bring this down. Delta x times the value of the function evaluated at the midpoints. Okay, that's just midpoints applied to this. That's just these values right there. Okay, so we say delta x in our case is pi over 8 times the value of this function at each of these, evaluated at each of these midpoints. So cosine to the 4th power of pi over 16 plus cosine to the 4th power of 3 pi over 16 plus cosine to the 4th of 5 pi over 16 plus cosine to the 4th power of 7 pi over 16. Right? That's just using the midpoints. You'd calculate all of this. Make sure that, please double check my number here, but make sure that your calculator is in the radians mode. Calculate all of these, raise them, don't forget to raise that to 4th power, each one. Add them together, multiply it by pi over 8, and you should get this value, 0.5890. And they said round it to 4 decimal places, and that's what I have. Okay. All right. So let's then look at other examples to make sure that we understand the definite integral. So in these series of examples, we want to express okay, so let's do a couple of examples of this. So we have we have this, we have limit of, express the limit as definite integral. Okay, so we're going the opposite. In these examples, in this example that we just did, right, we approximated this definite integral using the Riemann sum for n equals 4, right? Not as n goes to infinity, but n equals 4, using the summation. So in every example that we did so far, here n was 6, right? Remember that? So we're going the opposite way. We have been given a sum. We want to rewrite it, not calculate it, but rewrite it in the definite integral form. Okay, this is the given limit. Limit as n goes to infinity of the sum cosine of xi divided by xi times delta x over the interval pi to 2 pi. Okay, so solution of that is that this is easy, right? These are the upper and the lower limits of the definite integral. So it would be definite integral going from pi to 2 pi. We know what our function is here, right there. It's in front of us. Cosine of x, no longer x sub I, but just cosine of x over x. Instead of delta x, we have dx. So now, when you calculate the definite integral, you know what dx represents. It's the width, it's the infinitesimal width of each of those infinitely many rectangles in the Riemann sum as n goes to infinity. We did some basic examples, n equals 4 and n equals 6, so you know what we mean when we calculate the Riemann sum for n going to infinity, which leads to the definite integral. Those ones, those individual calculations that you saw, those were approximations of the definite integral. But as n goes to infinity, that approximation is much more exact. It becomes an exact value. Okay, so that's that. So this is the summation notation, or the Riemann sum, and this is the definite integral notation. Why don't I write that? So this is the Riemann sum notation. This is the equivalent definite integral notation. Okay, let's do another example. So here we're getting used to the notations, which is a really good thing, since mathematics is largely a language of its own. Okay, so we want to know, or we want to write the equivalent form of this Riemann sum times delta x over the interval, closed interval 1 to 3. Okay? All right. So the solution of this then, again, this conversion can easily be done. By the way, let me just quickly say that this is the Riemann sum notation. And then so we convert it. We say the lower limit of the definite integral is 1. The upper limit is 3 of this function without the sub i's, because sub i's are connected to this lower and upper limit of this sum, the range of this sum. We don't need that anymore, so we simply say x divided by x squared plus 4. And of course, delta x, which is the infinitesimal When you have n going to infinity, infinitely many of those rectangles, rather than 4 and 6, if you have infinitely many of them, then that delta x is very, very infinitesimally small. And when that happens, we call it dx. We no longer call it delta x. It's dx. When those intervals are infinitesimally or infinitely small, we call it dx. And then this is all they want us to do. And let me just mention that this is the definite integral notation. Okay, so here is the definition of the integral, and this is important because, you know, if you remember one of the first sections in this class, before we introduced methods of finding the derivative, one of the several exercises that we did, I can't remember if it was 5 point, one of those earlier sections, I can't remember what section number it was, but we applied the definition of a derivative to find the derivative, which was rather laborious, much more laborious than just applying the power rule or the quotient rule of finding the derivative of a function. But there was something called the definition of the derivative that we applied before we actually started using the techniques of finding the derivatives more efficiently. Now here we have this definition of the definite integral, and we'll do one, maybe two examples of finding the value of the definite integral using its definition. At least one example I have here, so that we just see how it works. But we don't do that normally. It's just we need to know how this works in relation to the its definition of the definite integral as it relates to the infinite sum or the Riemann sum. Then eventually we will use much more efficient ways of finding the value of the definite integral. But don't be surprised if we're applying the definitions to find the definite integral at first. We just want to make sure that we understand how the definite integral works. Okay, so here's the definition. I believe I more casually mentioned it earlier, but this is more formal. So the definition of the definite integral so we say that if f is integrable on some closed interval a to b, then we can say that the definite integral from a to b of f of x dx is equal to the limit of the sum as n goes to infinity, limit of, well, I should remember to put my sum notation here, limit of the sum, I going from 1 to infinity, to n, sorry, and n goes to infinity. So 1 to n, as n goes to infinity, where we have delta x, which is equal to b minus a over n. Of course, as you know, as n goes to infinity, then the width of those delta x values become very small, which represents the dx on the definite integral side of this equation. And xi is equal to a, the lower limit, plus I, or I is the number of the rectangle, first rectangle, second rectangle, and so on. However many rectangles we have, I times delta x. Okay, and let me just make sure that, so I is, everything is defined here. So I'll start from here. This one is the right endpoints of every integral, or interval, sorry, of every interval that is this, actually I should say, this is the right endpoint of the whole thing, xi that is. Okay, and what else do we have to, and I is basically 1, 2, 3, and so on. So I equals 1, 2, 3, and so on. And I think we've defined everything here. Yeah, so let me, so this is the definition of the integral. Very important, like that. And in conjunction to this, to the definition of the definite integral, let me mention again those things that I mentioned earlier, and this one, these summation formulas, these, when you apply the definition of the integral, definite integral, to approximating its value, then these sums might become very useful to you. So that's why it's so important. I don't mind rewriting it again. So let me write down what I just said. So important. Definite integral. The following sums may be very useful. So we don't want to forget about these. We want to keep them in the back of our head and remember them. So 1, and this is, as I said, I mentioned it earlier, but let's mention it here in conjunction with the definition of the definite integral. So you have them both on the same page. If you ever have to reference them, they're on the same page. So I has power 1, that is equal to n times n plus 1 divided by 2. That's one of them. The second one is when this I is squared, as I goes from 1 to n, that is equal to n times n plus 1 times 2n plus 1. And then over 6. Just look at the proof for one of these, even though we don't use that in this class. We don't use the proofs, but look at the proof for this one. It's really neat, clever, and easy to follow, and it gives you an idea about the proof for these other ones. That's all. So that. And then, so what else? And then we also have the one with I cubed, right? Oops, that square should be on the outside, sorry. So let me correct that. That's not the power of this parentheses, guys. That power is on the outside, as outside of this bracket. Okay, so it's on the outside. Like that. All right, so now that we have that, let's apply that, all of this, to an example. So it will help us understand how all of this ties together. Suppose so use the definition of the integral, which is this, right? This is, like I said, sometimes we are asked to use a definition, so we have to use that. And it's important, so let me, definition of the integral. To evaluate this integral. To evaluate definite integral from 2 to 5 of 4 minus 2x dx. Okay, that's what we want to do. So solution. Let's recall what the definition, right? That's the first thing we need to do. So recall that definition of the definite integral is as follows. Right? That's the definition of the integral. We'll put that away. So what do we need? To apply this definition of the definite integral, we need the delta x, and of course we need the xi as well, right? To evaluate this function at xi, we need to know what xi is, and we need to know what dx, for this problem, what delta x is. Okay, so let's calculate these. So in this case, I'm going to recall that, and then on the left side we have that. So let's substitute it. We have the definite integral from 2 to 5 of 4 minus 2x dx equals all of that. And then I, going from 1 to n. All right, that's that. And then f of x now first let's find delta x. So we need to find xi and delta x. Delta x is 5 minus 2, right, divided by n, basically. N goes to infinity, so we just say n. So 5 minus 2 divided by n, or 3 divided by n. That's our delta x. Okay? And then xi, let me go back to that. Yes, so we defined xi. So that's what we did. We defined delta x as the limits of the definite integral divided by n. That's what I just did. And xi's are these. So let me actually mention that too. So in this corner, I'm going to say delta x is equal to b minus a over n. and xi is equal to a, or the lower limit of the integral, lower limit of the integral, plus I times delta x. Okay, so delta x we already know, 3 over n, I, and then we can calculate that. Okay, so then using the, so we have the delta x, and now xi is equal to the lower limit of the integral, which in our case is 2, which is a, right? Let me box these. So we're using them here. So 2 plus I, right, times delta x. I is I times delta x, which is 3 over n. I'm just using that to find xi. So what do we have then? Xi, or x sub I, is 2 plus 3i over n. So what do we have? We have delta x here. We have xi here. Okay? We have everything we need. And so let's calculate or approximate the definite integral. So we have, I'll just write it here then, from here, using that. So we have the limit of the sum from 1 to n as n goes to infinity of f of the function of this function 4 minus 2x. But that's 4 minus 2xi now, right? Times delta x, because we're applying the definition, not the original definite integral. So we say f at xi, so let's see, so this would be xi, yes, so let me, so yeah, I'll do it step by step. So f at xi times delta x, let's substitute now. So we have limit, as I hope I can fit all this on this one page. And so I from 1 to n, f as that would be, so this is that function, 4 minus 2xi times delta x, which is 3 over n. 3 over n. Okay, so that xi now is this whole thing. Right? So let's do that. I want to make sure that so this looks okay. Okay, so now we're substituting for xi with that quantity, 2 plus 3i over n. All right, so that is equal to limit as two times all of that, 2 plus 3i over n times 3 over n. Okay, like that. That's our delta x. Okay, so that should be okay from like that. So this 3 over n is just a constant. I mean, it has there's no I in this expression, so we can pull it out of this and put it in front. We can do it later or now, it makes no difference. But let's do it anyway. So let limit as n goes to infinity of 3 over n, right? I just put that out in front of the sum, because the sum only applies to any term with I going from 1 to n. So we have then what do we have? We have 4 minus that. So distribute this. Minus 2 times 2 is minus 4 plus this 4. That's 0. And then minus 2 times 3i over n, it's minus 6i over n. So if you simplify all of this, particularly with this minus 2 times 2 is minus 4, adds to this plus 4, and they drop out, add up to 0. So we end up with this. We end up with we're going from 1 to n of minus 6i over n. Okay, and the 3n is now in front. Okay, that's after simplifying. And then minus 6 over n can also be brought out because it has no I in it, right? So any piece of this in the product form that doesn't have I in it can be pulled out of the sum. So let's do that. Limit as n goes to infinity of 3 over n times minus 6 over n of I going from 1 to n of I. Okay. So now recall, I was hoping maybe I can still fit it on this one page. I hopefully I can. So recall this piece, right? We just mentioned it. That piece is equal to that, right? N times n plus 1 over 2, that piece. So that's where we can use that. So recall that sigma I 1 to n, that piece is equal to n times n plus 1 over 2. Right? So n times over 2. And so that then we can, let me actually, I think I can bring this down a little bit. There is still hope I can still fit everything on one page. Okay, so let's come up here. Thus, now in this equation, for that piece, we're going to replace it with this. Okay, we're going to say that limit as n goes to infinity of 3 over n times minus 6 over n, right? That's what we have, times this piece, n times n plus 1 divided by 2. Right? All of that. So what do we have? We have minus 18 over n squared, right? So times n, so they cancel each other. So let's write it down here. Oh boy, I hope I can finish it on this page. So we have minus 18 over n squared, and then times all of that, times that, and then equals, after we simplify all of this, and we will get this. We get minus 18 over 2 times n plus 1 over n. That's after simplifying. This n squared is going to drop out, and that 2 becomes a denominator. So minus 9. And then let me start from here. Then we have limit of, so that'll be minus 9 times limit as n goes to infinity of, if we simplify that, what do we get? N over, separate that. So you get n over n plus 1 over n, right? So you get 1 plus 1 over n, and that piece, now we apply the infinity, you get that piece will become 0, So you get minus 9 times 1, or minus 9 is the final value of that definite integral. Okay, okay, so I barely was able to fit this on the screen like that. Okay. All right, so that's applying the definition of the definite integral to calculating, to approximating that quantity of the definite integral. So let's do, so that's calculating the definite integral using the definition. Let's use the area, because earlier we said that the definite integral is also equal to the net area, right? It was one of the, right there. It was one of our first slide. It was actually the first slide. And the definite integral, so that's the definition of the definite integral, which we casually mentioned it on the first page. And then also the definite integral represents the net area below or above the curve as shown in the figure on the next page, which was this, right? The minus area segment plus the positive area segment is equal to the definite integral. So let's use an example that makes use of that graphical representation of what a definite integral is. Okay, and so this was page, I think this should be page, so this would be page 9. So we want to evaluate the integral by interpreting it in terms of areas. Okay, so let's do that. So here's the example. We want to evaluate the definite integral from minus 5 to 5 of x minus square root of 25 minus x squared dx. Okay. Well, one of the properties that we mentioned earlier, right? Let me bring that back. If I can find it quickly. Oh, it was. I didn't realize that it was. Oh, maybe. Oh, there it is. Okay. This. Remember this? So the definite integral of the f of x plus or minus g of x dx is equal to, we can separate them like that. So let's do that. We have that, f of x minus g of x. So let's separate this using that property of definite integrals. So we have, that is equal to the definite integral from negative 5 to 5 of x dx minus the definite integral of negative 5 to 5 of square root of 25 square root of x, square root of 25 minus x squared dx, right? We can say that using the property. Now, the area representation of this segment, right? So the area of this segment, okay, let's I missed my ruler today. I'll just draw it freehand. So, like that. So the area representation of this, well, the area representation of this segment, and let me actually use of this segment, f of x equals x, that piece of f of x equals x, right? So this definite integral would be the net area of that function between -5 and 5, right? That's the area representation of what that function is. So this definite integral represents the area of between this line or this curve. In this case, it's a straight line that goes through the origin, dissecting the first and the third quadrant. So let me draw it instead of just talking about it. So it would go, I'll try. So this should dissect, even if I can't draw it freehand. Hopefully that's accurate enough. So this is just a line x equals y. Remember, x equals y, all the points on this line are equal. So 2 comma 2 is on this line, -5 comma -5 is on this line. But here we want to, I should actually put a dot here, here, and here, because it's from -5 to 5. So the area representation of that definite integral is this, from -5 to 5, and here is the net area would be this plus that, right? What do you think this would equal to? This plus that, these are equal because this is line f of x equals x, so x equals y. So these pieces are equal to each other. And if this is negative area, that's positive area, you get 0 because these two are similar, equal to each other, but opposite. So area equals 0 for this function. Okay? So that we said that the definite integral represents a number. Remember that in the beginning. So what that number represents is the area of the function that we're integrating, the area between that function and the net area of that function, the area between that function and the x-axis. So in this case, it would be area equals 0 for that. So what would that be for this? So then the area representation of this, I call the segment, but this function f of x equals square root of 25 minus x squared of this function or segment, then it would be, that's a semicircle, right? So let's draw that as well. It's the semicircle with radius 5. Oh, by the way, so this is f of x, this is x, this is f of x, and this is x. Okay? Of this function, and I will once again, so this is f of x equals square root of 25 minus x squared, that function. So hopefully I can draw this as best as I can. I don't know how accurate I can be, but -5 to 5. And let's say that is also 5. So this would be roughly this semicircle like that. Okay, so that area is going to be this region. And we know how to calculate that area, right? Pi r squared would be the area of the full circle, but this is half a circle, so it would be half pi r squared, r being the radius, which is 5. So, so area of that would be 1/2 times pi times 5 squared, or 25 pi over 2. Okay, so now that we have the area representation for each function, which definite integral represents, then we can carry out this simple operation. This side or this area minus that area, right? We're looking for the net area. So 0 minus that. That's the area of this segment. That's the area of that segment. This segment. 0 minus that. So total area then, or I should say, since we've been calling it net area, let's call it that. So net area is as follows. Like that. So it'll be 0, oops, make sure that like that, 0 minus 25 pi over 2 will be equal to minus 25 pi over 2. Okay, so that's the area definition of the definite integral. So let's do a couple of more some interesting examples. These last two examples have to do with applying the properties of the different integrals that we introduced. So suppose in this example we want to evaluate the integral this. Sine squared x cosine of x to the 4th dx. So we want to evaluate that. But if you remember the properties, or let me refer back to them, notice the lower and upper limit of this integral, right? They're equal. What did we say? I mean, this whole thing, remember, represents the area, the net area under the curve, and as it relates to the x-axis. So if the limits are equal, then there is no area, right? In order to area, we need to have a width. If there is no width, then we have 0. So this one is simply equals 0. So actually, solution, let me just explain it. Because the limits of the integral are equal, then we can easily say that the definite integral from pi to pi, or of sine squared x cosine to the 4th of x dx equals 0. Okay, using that property. Let's do one more example, again using the properties that we've mentioned. So given that we have this equation, minus 8, given that, then what is, we ask, what is the value of this? The definite integral from 1 to 0 of 3u square root of u squared plus 4 du. Okay. So what do you think about this? All right. So two things should catch your eyes immediately. One thing is that what we're looking, this definite integral that we're looking for is really that with the variables different. So instead of 3x, we have 3u. Instead of square root of x squared plus 4 dx, we have square root of u squared plus 4 du. Right? Instead of x, we have u. That's all. And equals that. We have this definite integral. We know that is equal to that. The other thing that should catch your attention is look at the limits of the integration. What we've been given has a lower limit of 0 and the upper limit of integration of 1, but this is reversed. So it's 1 to 0. And going back to the properties again, let me bring these back. Remember that this first one? And I should actually make that a different color so it stands out. If you have the definite integral going from a to b of some function, you can change the order of the limits of the integration. You can swap them by putting a minus in front. So minus then b to a of f of x to f of x dx. Right? Compare these two. So then, that's what we can do. We can really just replace, in what we want to evaluate, we can replace u with x, and we can swap the limits of the integration from this to that by putting a minus in front of this. So we can really say this. We can say that, first let's take it step by step. So this, what we're looking for, is equal to minus, now swap the order of, these red ink parts are very significant to notice, so I'm just writing them using red ink. And then 3u times u square root of u squared plus 4 du. Okay, that side, what we're looking for, is equal to that. Now compare this with that. Really, this is equal to that. If we replace back u with x, we get that. So let's do that. So we have minus 0 to 1, 3x. That's just replacing u with x. That's all. Like that. Right? So we know that this piece, sorry, let me change this to x. So let me use so we swapped from u, we went from u to x, so this has to be x as well. X. Now that piece, this whole piece is equal to that, right? Let me bring this down. This whole piece is equal to that. So we have minus all of that, 5 square root of 5 minus 8, right? That's what that is, equals that. So in other words, we have finally equal, distribute the minus, we get 8 minus 5, 5 times square root of 5, like that. Well, notice that so far, even though we've introduced the concept of the integration in chapter 5, we're still in both sections 5.1 and this one, 5.2, we're still focused on how the concept of integration relates back to the concept to the Riemann sum. So we're still solving examples that have a connection between the conceptual side of the integration and the numerical and the symbolic side of it. Eventually, we will get out of this and we will purely apply the techniques that makes life a lot easier. We will apply the techniques of integration as we go deeper and deeper into this subject, and for sure in calculus too. So for now, I'm glad that this session was useful. Thank you for watching the video until this point. For now, have a nice day, and I'll look forward to seeing you again next time.